Hello and welcome. So let's just carry on doing what we have been doing. We wrote down the variational procedure, which is here it will be psi h psi divided by psi psi, and it's a function of u1 and u2. So I will get two equations and I will have to solve these two coupled equations. That means I will write down a matrix which is 2 by 2 and diagonalize that matrix. There is so let's just write down psi again. Psi is u1 1 plus u2 u1 1 plus u2 into 2. Okay. Now let's see what this psi h psi gives me. It is 1 u1 plus 2 u2 operating on t plus v1 plus v2 and with u1 1 plus u2 2. Okay. So as I said in the previous page, remember that these energies are so 1 t plus v1 1 is epsilon naught and 2 t plus v2 2 is also epsilon naught, and that is what I am now going to use. Remember, I have to now expand this. So the expansion looks like this. So there is this u1 square into 1 t plus v1 1, for example, that is one term. Then u2 square 2 t plus v2 2 is another term, and so on and so forth. Right? There are other terms, you can write them down. Remember, we had chosen this definition. So 1 v1 2 is minus t. This minus sign is just a convention. Is generally these integrals turn out to be negative for most of the cases for nearest neighbors, and so this minus t is between 2 between v1 and, so it is a cross term. On left side you have 2, on right side you have 1, or vice versa, and I have taken t to be again a real quantity. So if you go ahead and do it, let me just write down the expression that you will get. This will be u1 square into epsilon naught plus u2 square into epsilon naught plus 2 u1 u2 into minus t. This is what you will get. Remember, there is a term which I have neglected here. You will come across this term, which is which is often called the cross term, which is this term that let me just write that term down. This kind of a term. So I have neglected a term of this type. So the term I neglected is 1 v2 1 and 2 v1 2. So what so this is so called cross term. So this term, actually these two terms, look what it does. It is E square by R minus say R2, and you have 1 on this side and 1 on this side. Now it is the proton number 2 having a Coulomb interaction with electron number 1 here. Okay. So that kind of term is being neglected, and vice versa. One electron number 1 having an interaction with the nucleus number 1 having an interaction with the electron number 2 here. So these cross interactions I have neglected at the moment. In this, if you calculated the matrix element in the previous page, you would also find those cross terms in this adding to this epsilon naught. Now I will justify later on why I am neglecting it, and they are anyway much smaller than the epsilon naught, as you can see, because the epsilon naught is the energy of the electron in this atomic orbital to start with, which is much more than the cross term between nucleus 1 and electron 2 and electron 1 and nucleus 2. Okay. So that I will neglect. So these kind of terms are not included here. Okay. So let us now see what we had. We had this is the numerator of this, and the denominator is simple. The denominator is will give me just the so you have U1 square plus U2 square into epsilon naught minus T U1 U2 twice T, okay, divided by U1 square plus U2 square. That will be your E variation. Okay. So that's the thing that we have to minimize. That's the energy we have to minimize with respect to U1 and U2. So okay, one can directly do it by taking the derivative of variational E var with respect to U1 and U2, but a simpler way to do this thing is just take the denominator to the left hand side, U1 square plus U2 square E var equal to U1 square plus U2 square into epsilon naught minus twice T U1 U2. Now let us take a derivative of this equation on the left and the right with respect to U1 and U2. So what do you get is 2 U1 E var. So I am taking a derivative with respect to U1 plus this quantity in the bracket times del E var del U1 equal to twice U1 epsilon naught minus twice T U2. Okay. Now as I said in the beginning that my variational scheme involves setting E var del U either 1 or 2 equal to 0. Okay. So that means this term vanishes. So I have the equation I have is U1 into E var equal to U1 epsilon naught minus T U2. So this is the equation I have for E variation for u2. Similarly, I will have a almost identical equation which is u2 E var when I take a derivative with respect to u2 and set del this quantity to be 0, this del E var del u2 equal to 0. So, that will give me u2 E var equal to u2 epsilon naught minus T u1. As I said, this is a coupled, these are two coupled equations which are equations between u1 and u2 which determines the variational. So, which will set which will give for me the if I diagonalize, I write it as a matrix and then I diagonalize it and I will get the eventual eigenvalues and the eigenfunctions. So, this can be written as E var into u1 u2 is vector equal to epsilon naught minus T epsilon naught into u1 and u2. You can check that this is exactly the equation that I had written down. Let us go back and see. This is the equation I have. E1 times E var is E1 times E naught minus T times U2. That is exactly reproduced by this matrix equation. So, of course, the energies that I will get, the eigenvalues of this matrix is basically the E plus minus equal to E0 plus minus T. Now, if T was taken as a, see what I have done is that epsilon naught minus lambda into epsilon naught minus lambda, this is equal to minus T square. So, this is equal to T square. So, that is the equation I have solved for lambda. So, that gives me this E plus lambda. So, these solutions of lambda I have written as E plus minus, and these are the solutions. If T was a complex number, I would replace T by goes to mod T. That is all that there is to be done if T were complex. But just for the time being, let us just take T to be a real part, and that's all I so that gives me the value of T is the difference of T that makes the new eigenvalues. So, what did I have? So, I had originally epsilon naught, 2 epsilon naught wave functions. Now, I have a wave function. We have two solutions. These are the two degenerate levels originally. Now, I have a level which is at epsilon naught minus mod T, the value of T. If T has been taken to be positive, because there is a minus sign that I have already put in. So, I can just write this as epsilon naught minus T and epsilon naught plus T. So, these are the two eigenvalues of this wave function of this problem. Now, because of this T matrix element that connects the two electrons in the two atoms, that is going to be the new eigenvalues of this problem. So, what do I do now? As I said, that now I will just put the two electrons which were here originally here. I had two electrons. I have to now put them here, and how do I put them? The way to put them is put them up and down, and this is singlet again. The singlet wave function is the one that stabilizes the energy. So, how much was the original energy? E original E initial was simply twice epsilon naught, and E final is 2 into epsilon naught minus T. So that 2 epsilon naught minus 2T, and that is again the 2T amount of energy. T is taken positive here, remember. So this minus 2T amount of energy is what one gains by doing this. This is interesting actually. This one could have guessed by even basic quantum mechanical principles, because if you have two protons, then if they come close by, the electrons now have a much bigger radius to move around, and we know in quantum mechanics that Heisenberg principle likes to delocalize things. The more you localize a quantum object, the more you pay in terms of its momentum, and that means energy. So delocalization is always favored, and it gives to lowering of energy, and that is exactly what this has done. More than that, it has also given us the new orbitals, which are what? The new orbitals are just the eigen functions corresponding to these two. So psi of psi 1 comma 2 is basically 1 by root 2, 1 plus minus 2. And if we know that you can actually do a direct calculation and check that for this Hamiltonian that I have written down, the plus sign gives you lower energy. It corresponds to the eigenvalue epsilon 0 minus T, epsilon naught minus T. So this is a symmetric wave function. This is the orbital part of the wave function. So the spin part now has to be antisymmetric, which is what I have written down here. Its spin part is a singlet. That is the solution. Actually, that is exactly what happens in hydrogen atom problem. Although the energies that I am writing down are not all kosher, this is just an approximation. There are terms we have neglected, but nevertheless the physics that you get is contained in this very simple minded description of a hydrogen molecule. So what has happened then? Basically what has happened is that you had two, for example, if I even started with 1s orbitals, these were the orbitals, these were the say 1s orbitals, two 1s orbitals. They talked to each other and formed two other orbitals. This is called the sigma. This is called a sigma orbital. This is the bond called the bonding orbital, the lower energy, and this is the anti-bonding orbital. And I put two electrons in here, and I gain a reasonable amount of energy. And the wave functions, if you look at the wave functions, are like this. The two atoms were here, and the antibonding wave function is somewhat like this, whereas the bonding one, which is a symmetric wave function, is symmetric with respect to the two nuclei. So from the original ones, which were the original wave functions were both like 1s, for example, and the final wave function is a two linear combinations. One is one has a node, the other one is symmetric, and the corresponding spin functions are singlet here, for example. So the ground state is a singlet wave function with a symmetric orbital part of the wave function. So this is actually the picture of a real hydrogen molecule, though as I said, the energies that we used are not perfect, they are approximations. There is just one more comment I would like to make, is that this cross term that I had written down originally, the 1 V2 1 or 2 V1 2, these I had neglected. One of the reasons is that this is small, much smaller, But the other reason is also that there are these two nuclei which also had a interaction between the two, R1 minus R2, and it turns out that this interaction between the two nuclei more or less cancels the contribution coming from these cross terms. These I called cross. So, neglecting the cross term was not a bad idea, but of course, neglecting the Coulomb interaction between the two electrons changes many things, and that is something that is not part of this scheme of things that we are dealing with. That is a very different advanced topic. So, we will not discuss that here, but for the time being this gives the picture that I have given gives me two states at epsilon 0 plus T and epsilon 0 minus T, and energy is gained by forming the molecule for hydrogen. So, that is what the message that you should carry back, and we will then consider a larger set of atoms, but before that we will do some analytical exact ideas. We will just discuss those ideas for a periodic lattice, because after all a lattice is a periodic structure, potential is periodic, and we will discuss a few things about that kind of a potential. Thank you.